Now, the second problem is how to avoid redundancy in such a system. So typically what happens is that we need to serve a new subscription. We look at what is currently done in the system, and we try to serve at best parts of the subscription based with processing that is already done in the system. So actually we try to add as few as possible, as few new operators as possible to the system. And for this we have to represent what is currently executed in the system. And we use representation in XML of metadata concerning the streams. This is stored in a stream definition database. Now, how does it work? We have an expression here, let's say, that is the active XML stream expression for the monitoring task that we consider, and we typically try to match sub-expressions with information available in the stream definition database. So little by little we try to match bigger and bigger sub-expressions to streams in the system. Okay, so hopefully in the end all the monitoring task is can be already is already available through a stream, and the user simply subscribes to this stream. There is no need to define new monitoring. So on this example, we have 3 tiers, and we have alerters that are communications. So incoming communications, outgoing communications, 1 alerter per tier, and these will create each a stream that is either processed or exported to other tiers. And if we have this new monitoring task, I don't know if it is very visible, but in the end, this new monitoring task could simply results in the stream S5 at P1. So there is no additional processing added to the system. Now, during the development of T2T Monitor, we have figured out that actually what is extremely important are the stream processors. So we paid attention to them. We have developed a method for building complex stream processors that is called AXLog. And this is the marriage between ActiveXML and Datalog. ActiveXML documents is the support of the method, and Datalog are the techniques that we are using. Now, this has been, of course, motivated by P2P Monitor, but the technique can serve to building data integration and mashup systems for distributed query processing, and in general for systems that manage data streams in a distributed context. Okay, so typically here we have an active document that has input streams of updates. This is very important because the updates arrive at particular places into the document, and these are marked places that are called functions. Now we have views that consist in 3 pattern queries, and each time an update arrives, it typically modifies the document, so possibly the query result. And we need to maintain the query, so to produce a stream of updates. So we have a problem that is view maintenance of our XML documents, and we try to solve this in an incremental way. I'll show you next how. The model is the following. We have a document that is unordered, unranked, labeled, and reduced tree. This reduced tree means that there are no two-siding subtrees that are isomorphic. Now, for the updates, we consider insert and use. Those have as context a function call. actually function calls are always prefixed by question mark. So here in the document we have one function called that is f. Now, for the insert, suppose that we have a tree that consists of G with a child A. Inserting it at function called f actually means adding it as a sibling to the function called f. Delete, actually what happens is that we have to check this condition against siblings of the function, and those subtrees that match the conditions are deleted. Now the queries are two-pattern queries. They return a set of updates and a set of tuples. And the tuple is typically easy to transform into an XML document by using a query. So before the insert, the query result was the empty set. After the insert, the query result is a tuple that is an. We use a restriction of Axlog model that is monotone. It has only some insertions. Queries are positive. Streams never terminate. Functions do not bring new functions, and there is no typing. So what we try to do, I'll show you on this example. We have a query, okay, and a document. Actually, functions are very important here. If you look, the A of the query is already in the document, the B also, the C also, and what is missing is the D. And the D, well, only the G function can bring it. So the function f is useless, and the only thing that interests us from G are the updates that are rooted on D. Okay, so we can filter the updates of G to obtain only the D-rooted updates. Okay, so we have an algorithm that is Axlog. It uses techniques of data log for XML query processing. It uses differential, that is a technique for that avoids recomputation of relational views. It uses magic set, and it also uses novel notions like satisfiability, scenarios, and relevance. And I'll talk about them right away. So how does it work? At compile time, it tries to understand what are the streams that are really important for the view, and how these streams are important, meaning what kind of updates they could bring that could actually impact the view. And in a distributed setting, it is important to block the arrival of useless data, and we use for this stream filtering techniques. Now, the first technique is satisfiability. Well, satisfiability for the tuple means that the tuple actually has a chance to appear in the output of a query as evaluated on some instance of a document. So we are actually interested in possible results of the query when the document evolves. Okay. Now, a scenario is typically attached to a satisfiable tuple and actually says how the tuple has become satisfied. I mean, how would become satisfied. So what kinds of updates are necessary, and on which streams, so that the tuple becomes satisfied. Now, the relevance typically consider each function and looks if it can impact the view or not.